All right, so here we're going to examine the modes of operation for MOS transistors. So here again, we start with our MOS transistor. We have the gate, we have our source and drain diffusions, and importantly, we note that the channel underneath the gate is completely depleted of any carriers. Now this occurs when VGS is less than the threshold voltage, VTH. And in this mode, we say no current flows. Now in the triode region, we're going to add a couple of voltage sources here, and we're going to explicitly say that the one that's connected between the gate and the source, VGS, is greater than VTH. And we're also going to say that VDS is greater than 0. So here we have our drain electrode. Now, because the gate to source voltage is greater than the threshold voltage, we'll have formed a channel underneath the gate. In this case, free electrons from the bulk will have been drawn up by the electric field that's created by that VGS. We say in this case that the channel is inverted. It's gone from being primarily consisting of p-type materials to free electrons that can form a channel between the two N+ regions. And this is due to the vertical E field from VGS. The vertical E field from VGS causes accumulation of carriers in the channel. Now, the drain to source voltage creates a lateral E field due to that VDS that causes the carriers to move from the source to the drain. The carriers all carry a charge along with them, and so we have a current. Now note, we'll have electrons going from the source to the drain, so the convention is to say that we have a positive current flowing from the drain to the source. Let's look at the details of this current just a little bit more. Here we have a 3D view of our transistor. You can see that it has some width, some length, and the oxide has some thickness. Q sub y is the charge density at position y in the channel. C sub ox is the oxide capacitance, which is equal to, per unit width, which is equal to epsilon r times epsilon naught divided by T ox. Epsilon r is the relative permittivity of the oxide material. If it's silicon dioxide, it's approximately 4.1. Epsilon naught is the permittivity of free space. So this tells us something about the capacitance of the channel. Now we know that charge is the product of the capacitance times the voltage. So we can say that our charge at position y is the product of C ox times the voltage at position y. Now we know that current that flows is going to be equal to this charge times the total width of the channel, again projecting this into a second dimension, times the velocity of the carrier. Now we know that the velocity of the carrier is proportional to the mobility and the electric field that the carrier is under. So we can expand this out just a little bit. So our drain current is now mobility times the electric field, the lateral electric field, times the width of the device times Cox times the voltage in the channel at position Y. Now we can integrate across the length of the channel. We can integrate the voltage across all positions in the channel. And if we carry this integral out, we would find that the drain current is equal to mu times Cox times W over L times VGS minus VTH times VDS minus VDS squared over 2. This is the current of the transistor when it's operating in the subthreshold, in the triode region. If we were to plot this current, we would see that it's parabolic. And that theoretically, after it reached VGS minus VTH, the current would start to fall. But indeed, that does not happen. In fact, the current we know stays at the same level after this value of VGS minus VTH. So here we have the devices in the triode region. And what happens ultimately in the saturation region is that the transistor goes into the saturation region. And this happens when VGD is less than VTH. What's happening here is the channel gets pinched off at the drain. Once the channel is pinched off at the drain, the current stays constant. In other words, the drain to source no longer has any influence on the output current. Now, we can plot here the square root of the drain current as a function of the VGS. We would see that it would look something like this. And if we substitute VGS minus VTH for VDS in the triode equation, we'll come up with our drain current in the saturation region. Here we have the ID sat is equal to 1/2 mu Cox W over L times VGS minus VTH squared. Again, we note that VGS minus VTH is sometimes called the overdrive voltage, or VOV. Now we can make one minor modification to this. We can multiply this whole quantity by 1 plus lambda times VDS. And this lambda is a parameter that estimates the output resistance of the device. It's a similar quantity to the early voltage of the bipolar transistor. In fact, it's similar to 1 over the early voltage of the bipolar transistor. Now, one more thing to note. Below the threshold voltage, we say the device is in cutoff and no current flows. But for any real MOS, some current does flow. It's called subthreshold current. All right, we'll stop there for this video, and we'll pick up in the next video with the small signal model of the MOS transistor.